Today we are going to see the citric acid production. Citric acid is an organic acid. There are many types of organic acids like succinic acid, citric acid, acetic acid, propionic acid. Usually these organic acids are widely used both as additives in the food industry as well as in the chemical industry as well as in the pharmaceutical industries also. So, you have many different types of organic acids which are derived directly from the glucose. For example, the gluconic acid or the acetic acid, lactic acid, even you can have oxaloacetic acid or you can have the citric acid too. So, usually the commercial production of citric acid was carried out in order to satisfy the demand of the food and beverage industry as well as the pharmaceutical industry. So, in 1929 there was a production of only 5,000 tons, but it was increased to 350,000 tons in 1982. So, this was the demand of citric acid which was usually has to be satisfied by the worldwide. This citric acid is has been known as a natural plant substance since the end of 19th century. Since 1893, scientists have known that it is produced by the filamentous fungi. So, the history of citric acid production from the fungus were known since 19th century, and fermentation were usually carried out in the vats in 1930s. In South America and Mexico, there were also small factories which usually produce citric acid from the unripe citrus fruits. It constitutes near about 7 to 9% of citric acid. But today over 99% of world's output of citric acid is produced by the microorganism itself. So, firstly they were produced from the citrus fruits. But nowadays 99% of the citric acid, world's citric acid demand is satisfied by the fermentation process. Citric acid C6H8O7 is a weak organic tricarboxylic acid which is found in the citrus fruits like lemons, mandarin, oranges, tomatoes, beets, etc. So, they contain sufficient amount of citric acid and they are usually classified as the acid fruits. Citric acid is produced by three methods of fermentation, that is the solid state, then submerged and the liquid fermentations. So, in detail today we are going to study about the citric acid fermentation by solid surface and submerged fermentation process. Usually citric acid is used in making the fruit juice extracts or the candies or ice creams or marmalade is enhanced, and usually citric acid is used as a preservative as a preservative for beverages also as well as in the food industry. The pharmaceutical company it utilizes 10% of the citrate as a source of iron, and citric acid as a preservative for the stored blood. So, citric acid is also used as a preservative for storage of blood, as well as it is used in ointments, then tablets and in cosmetic preparations also. And in chemical industry 25% of citric acid is used as a antifoam agents or in the cleaning agents as a softener and in the treatment of textiles also. In metal industry also, citric acid is usually used as a metal citrates. Okay. So, citric acid is also used in the detergent industry because it replaces the polyphosphates. But since the price of the citric acid is higher than the polyphosphates, nowadays it is not used in the detergent industry. The history of citric acid production. In 1784, W. Scheele, he isolated citric acid from the lemon juice as the calcium citrate, and later on he treated it with the sulfuric acid to give the citric acid in the liquid phase form. In 1930, Jaworski patented a new strain, that is Aspergillus niger, which produces the citric acid. And in 1917, Curie opened the way for industrial production of citric acid via fermentation process using a new microorganism. And in 1960s, practice of submerged fermentation gained popularity and citric acid was produced by the fermentation processes. So, what are the different microorganisms which are employed for the citric acid production? So, there are many strains of microorganism. They excrete traces of citric acid as a metabolite of primary metabolism. Means citric acid is a primary metabolite which is usually excreted by the microorganism. Various strains of genera belonging to the fungi, yeast and bacteria were reported. So, the fungi basically belong to that is the Penicillium, genus Penicillium and Aspergillus. So, in Penicillium we have Penicillium luteum, Penicillium purpurogenum, Penicillium stricticum, Penicillium xanthilinum, Penicillium citrinum, Pacillomyces divaricatum, Mucor piriformis, Trichoderma viride, and yeast you have the Saccharomycopsis lipolytica, you have Arthrobacter paraphernaeus and cornybacterial species. Also you have the Arthrobacter paraphernaeus and cornybacteria, and you have compared to the Penicillium strains, Aspergillus niger or the Aspergillus species is extensively used to produce more citric acid per unit time. So, only the mutants of Aspergillus niger and the yeast candida have been extensively utilized for the citric acid production. So, now we will come to the biochemistry. So, citric acid is excreted from the cells in response to the unfavorable condition caused by increased level of tricarboxylic acids. So, when the citric acid is eliminated or excreted out, when there is a increased level of tricarboxylic acids. Okay. A crucial prerequisite for overflow of citric acid from Aspergillus niger cells is therefore increased level when the Krebs cycle is continuing and is producing the intermediates usually because of the anaplerotic reactions. So, we are going to see in detail what are these anaplerotic reactions. Citric acid is the primary metabolite or the metabolic product, and usually it is formed by the citric acid cycle. So, glucose is the main carbon source which is decomposed or degraded to produce the citric acid. So, in many microorganisms 80% of the glucose is usually used for citric acid biosynthesis and is usually carried out by the Embden-Meyerhof-Parnas pathway, and 20% by reaction of the pentose phosphate cycle. So, during the growth phase, usually the relationship between these two pathway is 2:1, means 2 times the EMP pathway takes place and the citric acid is produced, and only at the ratio of 1 the pentose phosphate pathway takes place. So, in citric acid producers all the enzymes of EMP pathway are produced and it is present throughout the fermentation process, and the activity of the pathway is usually regulated in a positive manner, and the synthesis of citric acid is taking place in presence of phosphofructokinase, but it is negatively inhibited by another enzyme which is called as the pyruvate kinase. In glycolysis usually the glucose is converted to phosphoenol pyruvate. This is your phosphoenol pyruvate, and this phosphoenol pyruvate is forming the pyruvate, and from pyruvate in presence of enzyme pyruvate decarboxylase you will get the acetyl CoA, and this acetyl CoA in presence of oxaloacetate. Acetyl CoA is a 2 carbon compound and the oxaloacetate is a 4 carbon compound. This 2 plus 4 it becomes a 6 in presence of citrate synthase enzyme. So, the acetyl CoA and the oxaloacetate in presence of citrate synthase enzyme usually it results in the production of citrate. Now, what happens? This citrate, as you know, this is a tricarboxylic acid cycle or the TCA cycle or the Krebs cycle. So, citrate is then that is isomerized to isocitrate, but in this case you will see that there is no production of alpha ketoglutarate, because the alpha ketoglutarate dehydrogenase enzyme is absent or it is not present, and therefore directly you will see that the another enzyme isocitrate synthase, the citrate synthase activity is increased by the factor of 10 usually during the production of citric acid. However, the aconitase or the isocitrate dehydrogenase activity is usually reduced when compared to the trophophase. So, usually this is the idiophase. Idiophase means it is the initial phase where the citric acid production is done through the TCA cycle. But the citric acid is not usually produced in the higher amount. Higher amount of citric acid is produced only in the trophophase. So, in trophophase citrate synthase is activity is increased by tenfold and there is accumulation of citric acid. Citrate synthase, however, it cannot be solely responsible for the citric acid production, because usually the activity of tricarboxylic acid is usually maintained and citric acid is produced, but if the citric acid is removed from the fermentation broth, then the citric acid production is ceases or it does not produce any more citric acid. So, there is another pathway, that is you call it as the anaplerotic reactions, and these anaplerotic reactions connects with the TCA cycle. So, in the absence of glucose there is the glyoxylate which continues the citrate synthase. So, here we will see that the citrate is converted to isocitrate, and instead of going to the formation of alpha ketoglutarate and succinate, this isocitrate is forming the glyocyclate, and this glyocyclate then forms the malate, and then from malate you will get the oxaloacetate, and again the citric acid is produced or the citrate is produced. So, in presence of enzyme glyocyclate cyclase, you will see the formation of glyocyclate, okay, and this particularly from the malate to the oxaloacetate, malate dehydratase is used, and it converts the malate to malic acid to the oxaloacetate, and then oxaloacetate is converted to the citric acid. So, there are 3 types of anaplerotic reactions. The first anaplerotic reaction is carried out by the pyruvate carboxylase enzyme. So, from phosphoenol pyruvate we get the pyruvate or the pyruvic acid, and pyruvic acid in presence of pyruvate carboxylase enzyme, it utilizes the carbon dioxide, and it is directly converted to the oxaloacetate. It is oxaloacetate, and this oxaloacetate is converted to the citric acid. This is your first anaplerotic reaction. The first anaplerotic reaction is dependent on or it is dependent on the requirement of magnesium ions and the potassium ions, and acetyl CoA, as already we have bypassed here, the acetyl CoA is not used for the formation of citrate. Instead, the pyruvate is directly converted into the oxaloacetate and is converted to the citric acid. The second anaplerotic reaction involves phosphoenol pyruvate carboxykinase. So, this is your second anaplerotic reaction, in which the phosphoenol pyruvate, in presence of carbon dioxide, ATP is also synthesized and it is converted into oxaloacetate. So, this is your second anaplerotic reaction, but this reaction usually involves or takes place in presence of ADP, and it requires Mg 2 plus ion, Mn 2 plus ion, K or K positive and ammonium ions. So, if acetate or higher aliphatic compounds such as N-alkanes are usually present as a carbon source, then there is a third anaplerotic sequence which is taking place in the Aspergillus niger, and this is, as already I have explained you, this is in the absence of glucose. Usually the glyoxylate cycle takes place and the isocitrate lyase enzyme converts this isocitrate into the glyoxylate, and this glyoxylate is converted to the malate, and then from malate to the oxaloacetate, and you will get the citric acid production. This is about the citric acid production or the biosynthesis of citric acid, and now we will see the yield of the citric acid. The citric acid production usually takes place in the trophophase. Usually when the glucose is added, the mycelial growth occurs, or the Aspergillus niger grows, means the mycelium grows at a quantity, and later on in the trophophase only it starts producing the or excreting the citric acid. So, theoretically that is 123 gram of citric acid, 1 hydrate or 112 gram of anhydrous citric acid per 100 gram of sucrose is usually produced. So, but however, when we go for obtaining these yields practically, due to some loss during the trophophase also, you will not have the exact 112 grams of anhydrous citric acid per 100 gram or 123 gram of citric acid 1 hydrate form. But this is the estimation which usually shows that from 100 gram of sucrose, usually you get 123 gram of citric acid 1 hydrate. Citric acid production is usually influenced by the trace metal ions like magnesium, manganese, or you have the potassium. So, citric acid technology usually when you have a limited quantity, or if the satisfaction of Mg2 plus or copper is not satisfied, then the citric acid is not produced properly in the proper yield. So, in the absence of iron and magnesium also, usually this iron and magnesium, if it is present in the higher amount, that is in the higher parts per million amount, then usually it decreases the yield of citric acid. So, ions in higher concentration than 1.5 mg per liter strongly affects the cellular morphology by promoting the unproductive filamentous mycelial growth, and therefore the citric acid production is reduced. 1 microgram per liter of manganese could completely ruin the production yield because the organism's morphology to switch from the microbial pellets known as citric acid productive form to unproductive filamentous form will take place, because the yeast, that is the fungi, has to be in a proper mycelial form, that is in the growth of that particular, we have called it as a idiophase growth phase of that fungi, so that in the tropophase it will start producing the citric acid in a greater yield, having the greater yield. But if you are increasing the iron concentration or the manganese concentration, then usually it produces the unproductive form of fungi, that of aspergillus filaments, and you will not get a proper yield. But magnesium is required in the concentration of that is 2 ppm when you are using 15 to 25% of fine sugar or the pure sugar, that is in the form of a glucose. But if you are using the cane molasses or the other substrate molecules, then 0.2 ppm of magnesium promotes the citric acid production. Apart from these trace elements, also you require the copper, zinc and molybdenum for the citric acid. The fermentation media is usually constituting the different types of sugars. Usually the basic substrate which is used for the citric acid fermentation in fermenter plants or the bioreactors, when you are using a surface method, then it is the beet molasses or the cane molasses. But when you are using fine sugar or the pure form of sugar, usually 15 to 25% sugar solutions are usually used in the fermentation media. Fermentation plants using submerged fermentation can use not only the beet or cane molasses, but the substrate of higher purity such as hydrolyzed starch, or they can use the pure glucose, as I have already explained you, 15 to 25%, or they can use the raw sugar, that is it can be a purified and condensed beet or cane juices also. And you have many different substrates which are commonly used, like beet molasses, cane molasses, sucrose, syrups, starch, hydrols, alkanes are even used. Alkanes are the hydrocarbons which are also used for the citric acid productions, as well as oils and fats are used as a substrate for the citric acid. If starch is used as a substrate, then the amylases are produced by the Aspergillus niger, and this solubilizes the starch. However, if you are using a hydrolysate or the syrups, then you have to carry out the preliminary treatment with either the precipitants, or you have to carry out with the cation exchanges, so that you can remove the cations. For elimination of metals, usually when molasses are used as a substrates, usually before sterilization of the fermentation media, calcium hexacyanoferrate it is a hexacyanoferrate is primarily used to bring about the metal precipitation, so that the metal ions get precipitated out, and the citric acid production is increased by removal of the metal ions. Besides the composition of the nutrient solution, usually you have to control the pH also. So, during the EDO phase, the pH is maintained at the pH below 3 in order to suppress the oxalic acid or the gluconic acid formation. But during the tropophase, where the citric acid is produced, usually the pH is kept at the pH of 5. So, in the first 48 hours of trophophase, the pH falls to below 3 because of the that is metabolism of the ammonium ions. The pH is becoming that is acidic, but for better control of yield in the submerged cultures, usually the tropophase and idiophase, they are separated by the pH unit of 2 once the mycelial growth has been ceased. So, when the fermentation is taking place, and usually when the that is the fungi is in between the idiophase and the tropophase. So, in when the before the start of that tropophase in which the citric acid is produced, that is within the 48 hours of tropophase, usually you have to keep the pH having very much control, so it has to be kept at the pH of 5, and so that the maximum yield of citric acid is being produced. So another benefit of low pH is there is a decreased risk of contamination in the initial stages, because in the EDO phase, when your pH is below 3, naturally there won't be any contamination problems, so that the citric acid being produced is produced in the higher pure form, and there will be no contaminating bacteria which may contaminate and will not result in another fermentation product formation. Citric acid is produced by two different processes, that is the solid state or the surface process and the submerged processes. So surface processes, they were further subdivided according to the state of the culture medium, that is the solid or the liquid. That is the solid state fermentation or the liquid state fermentations, but they were using the surface areas. Two types of submerged processes are also used, that is the stirred fermenters are used, and the second one is the airlift fermenters, which are used for the submerged fermentation processes. Solid state fermentation was firstly used as a surface fermentation for production of citric acid using the rice, that is the rice straws or the rice brands by the Japanese people, and they called it as koji fermentation, KOJI fermentations. And usually a maximum of 500 tons per year was produced, that is through the surface fermentation process. But later on, these three, that is the airlift fermenters or the submerged fermenters or the liquid fermentation processes were used. Now we have different types of submerged fermentations. Either it is carried out in a fed batch process, or it can be carried out in a continuous fermentation. So citric acid fermentations, now it can be usually produced by employing immobilized Aspergillus niger cells on various kinds of carriers like glass or polyurethane foams, or entrapment in the calcium alginate beds or polyacrylamide gels, agarose, cellulose carriers, metal screens or polyester belts also. So usually earlier they were using the Aspergillus nigers as it is, but nowadays they are entrapping, they are immobilizing in various support matrices, and they are using it. Now we will see in detail the surface fermentation process. The fermentation media contains the molasses substrates. Usually it contains 15 to 20% of sucrose and added nutrients, which is acidified with phosphoric acid to the pH of 6 to 6.5, and then it is heated at the temperature of 110 degrees centigrade for 15 to 45 minutes. Usually the potassium hexacyanoferrate, as I have already mentioned in the previous slides, it is added to the hot substrate to precipitate and to complex with the metal ions. So this metal ions like ferrous, manganese and zinc, so that this particular metal ions will not act as a inhibitor or the metabolic inhibitor, and it usually influences, usually when it is not acting as a metabolic inhibitors, it will not restrict the growth and mycelial production of the fungi, and therefore it promotes the citric acid production. Inoculation is performed in two ways. As a suspension of conidia added to the cooled medium. So later on the medium is cooled, and then the suspension of conidia is added if you are using a penicillium, or you can add the spores of the Aspergillus niger to the cooled medium. And this medium, when it is added, it has to be mixed with the sterile air also, because air is very necessary for the growth promotion. and the spread of the spread as an aerosol over the trays. So the sterile air is circulated over the trays, since it is a surface fermentation. The temperature is usually kept at 30 degrees centigrade during the fermentation by means of air current, and usually during the fermentation you will see that if the carbon dioxide content is greater than 10%, then you have to remove the carbon dioxide. So this condition is also taken into consideration, that you don't allow the excess of carbon dioxide to get accumulated. So you have to see the passage of sterile air, as well as you have to control the carbon dioxide content also. So within 24 hours of inoculation, the germinating spores start forming 2 to 3 centimeter cover blanket of mycelium, which is floating on the surface of the substrate. So you will see a thick mat of that is penicillium, white colored penicillium, or you can see the aspergillus mat, and as a result of the uptake of the ammonium ions, the pH now falls to 2. So you have to now maintain the pH in the tropophase, so that in the tropophase the citric acid is produced in the higher amount. Then the fully developed mycelium, it floats as a thick white layer on the nutrient solution, and usually the fermentation stops after 8 to 14 days, and then you have to recover the mycelium to extract the citric acid. So this is how the surface fermentation process takes place. The next we will see the solid state fermentation. So in solid state fermentation, the solid substrate is usually soaked up with water up to 65 to 70% of water content, and after the removal of excess water, the mass is undergone a steaming process, that is for the sterilization purpose. The sterile starch paste is inoculated by spreading the Aspergillus niger conidia in the form of aerosols or as a liquid conidia suspense over the substrate surface, and then the pH of the substrate is about 5 to 5.5, and the incubation temperature is 28 to 30 degrees centigrade. Growth can be accelerated by adding the alpha amylase, because since we are using a starch, and if we are adding alpha amylase, then the starch hydrolysis will take place at a greater extent, and therefore the fungus even though the fungus can hydrolyze the starch, if you are adding the alpha amylase, it will usually promote the starch degradation, and because of that usually you will get the glucose, and then this glucose can be converted directly to the citric acid via TCA cycle or by the anaplerotic reaction. So during this, the citric acid production usually the pH value drops to below 2. The solid state surface process, it takes place, that is this fermentation, solid state fermentation takes place only in only 5 to 8 days at the and at the end of this entire fermentation process, the citric acid is extracted, and other mechanical ways are also used to recover the citric acid from the cells. So it is present, citric acid is present in the cells, you have to recover it. Now we will see the submerged fermentation. In submerged fermentation, the substrate which is used is the beet molasses, that is 12 to 15, it contains 12 to 15% of reducing sugar content. You have all the nutritive salts such as the ammonium nitrate or the potassium dihydrogen phosphates, they are also added, and usually the pH is maintained at 5.5 to 5.9. In this submerged fermentation, submerged means usually the organism is found dipped inside the nutrient or the fermentation broth. In surface means it is floating on the surface of the nutrient medium, and solid state meant you are using the substrate which is a rice bran or the wheat bran or anything like that, and the mycelial mat is growing on the solid surface. So in submerged fermentations, you see that the process is running in one or the two stages using hydrophilic spore suspensions or the germinated conidia from the propagator stage, and usually the amount of spores which are added is 5 to 25 into 10 raised to power of 6 per liter of the substrate. So, whatever the fermentation media you are using, you have to add 5 to 25 into 10 raised to power 6 per liter of the substrate, that is the spores which are found in the 10 to the power of 6 per liter of your substrate. The development of the hyphae and the aggregation generally requires a period of time, that is it requires 9 to 25 hours, and usually the temperature is 32 degrees centigrade. So, mycelia aggregation and spherical pellets are usually formed, and the productive form can be detected after 24 hours of inoculation. So, after doing the inoculum or after addition of the inoculum, say after 24 hours, you can see the productive form of mycelium which starts producing the citric acid. So, when the citric acid is usually accumulated, citric acid is accumulated, there results a change in the pH, and initially it was 5.5, now because of the citric acid production, it has the pH has reduced to 3.5 for beet molasses substrate and 2.2 for the sucrose substrate. If you are using sucrose as a substrate, then the pH of the medium reduces to 2.2. So, fermentation usually the submerged fermentation lasts for 6 to 8 days, and later citric acid is purified from the mycelium. So, you have many different factors which are affecting the citric acid production. So, what are those factors which affects the citric acid production? So, that are the concentration of the carbon source. So, if you are using a beet molasses, then the citric acid production yield is different. If you are using a starch, then it is different. If you are using the carbons like and alkanes, then also the citric acid production is different. Then nitrogen and the phosphate limitation, if the nitrogen source is limited, means if you have only a lesser amount of ammonium ions added, then also it will result in inhibition and the citric acid production yield is lowered down. Then the pH also, if it is greater than 5, then the citric acid will not produce properly. Similarly, the aeration has to be in a proper way, otherwise the citric acid will not be produced in sufficient amount, and as well as the trace elements like iron and manganese, they have to be supplied in a appropriate measures, otherwise it will be metabolic inhibitors. And also the lower alcohols, if the alcohols are used, then also you will see that the citric acid production yield will be differing. So, now we have already seen what are the production processes of citric acid production. Now, we will see how the product is recovered, that is how the recovery of citric acid is done. So, the first step is separation of the biomass from the fermentation broth. So, we have to remove the mycelial mats from the solid surfaces or from the surface fermentations processes, or if it is a submerged process, then you have to separate the biomass from the fermentation broth. Then this separated mycelia, they retain 15% of citric acid formed during the fermentation. So, it is having near about 15% of citric acid. Now, according to the production processes, if it is a surface process, then usually the fermentation fluid is drained out, and then hot water introduction is done to wash out the remaining citric acid from the mycelial mat. So, you have to wash the mycelial mat in order to get the citric acid, because citric acid is excreted out. Then this filtration cake, that is not more than 0.2% of citric acid, it is dried to yield a protein rich feed. So, even if this filtration cake is discarded, that filtration cake is cannot be, means the citric acid cannot be 100% recovered from the filtered cakes, and this filtered cake is carrying the 0.2% of citric acid, but this 0.2 citric acid can be dried along with the protein rich, and it can be used as a animal feed. But in the submerged processes, usually you have to heat the mycelium at 70 degrees centigrade for 15 minutes in order to coagulate the proteins, and then the oxalic acid removal is usually carried out by adding calcium hydroxide that is it is having a pH of 2.7 to 2.9, and the temperature at which the oxalic acid is removed in the form of calcium oxalate, calcium oxalate, which is precipitated out at 70 to 75 degrees centigrade, and then these precipitates are usually separated out by centrifugation. After oxalic acid removal, then we have to go for precipitation of citric acid, means you have to recover the citric acid. So, what is the recovery technique? So, then the oxalic acid is removed by centrifugation, and whatever the liquid form is there, that liquid form is containing your citric acid. So, this citric acid is then precipitated in the form of tricalcium citrate by addition of lime to the citric acid solution. So, when you are adding a lime, calcium hydroxide is the lime. So, it is means your citric acid is precipitate as tricalcium citrate. And to obtain the large crystals of high purity, usually the milk of lime containing calcium oxide is added gradually at a temperature of 90 degrees centigrade and pH maintained at 7. So, there will be minimum loss of citric acid because of solubility of the calcium citrate, which is usually 4 to 5%. Okay. So, calcium citrate is then filtered off, and subsequently it is treated with the concentrated sulfuric acid. So, concentrated sulfuric acid is 60 to 70% which is used, and this is you call it as that is the citric acid sulfate. And then this filtrate 25 to 30% citric acid, it is treated with the activated carbon to remove the residual impurities, or they may be purified in ion exchange columns, and you will get the purified crystal forms of, that is citric acid. So, this purified solution is then concentrated in the vacuum evaporators at the temperature below 40 degrees centigrade. Why 40 degrees centigrade is used? Because if you use the higher temperatures, it will bring about the caramelization. So, you will not get a white crystals of citric acid. So, because of this evaporation, the crystals of citric acid are usually obtained. Then the drying of the citric acid monohydrate, as we have said that citric acid 1 hydrate is the monohydrate, is obtained by using the rotary drying equipments, or you can use the fluidized bed dryers. And this form of citric acid, now it can be packaged and then it can be sold to various industries like commercial, cosmetics, commercial industries like food and beverages, or you can use it as in the pharmaceutical industries or in the medicine also. You have disadvantage of recovery of the purification process, that is because large amount of lime is required in order to recover the product, as well as the formation of large amounts of liquids and solid waste are also there. So, these are the disadvantages of recovery of the citric acid fermentation. You can use this another methods also for the by solvent extraction. The process can be applied when fermented must contain low amount of impurities. So, when the citric acid produced is containing low amount of impurities like trioctylamine or amine citric acid complex, or you have the aliphatic alcohols, ketones or ethers, or organophosphorus compounds like tri and butyl phosphate or alkyl sulfoxides. So, usually solvent extraction is carried out. Citric acid then is recovered from the extract either by distilling of the solvent. So, simply distillation mechanism, you can evaporate out the solvent and then you can obtain the citric acid. So, the aqueous solution purified citric acid is subsequently crystallized by the concentration process. You can also use the another method of recovery and purification, that is the ion exchange. So, the efficiency of ion exchange separation process may be greatly enhanced by applying this simulated moving bed counter current flow system. So, you have many different counter current systems, that is the ion exchange counter current systems in order to purify your citric acid. But here also you have a disadvantage of this technique, because elution of citric acid from the adsorption bed may require large amount of desorbent. Means we are allowing the citric acid to adsorb on a particular bed. Now when you try out to remove or desorb, means to remove out, then it requires a desorbent, and this desorbent is required in higher amount. So this is one of the disadvantage. You can use the liquid membranes also, liquid membranes containing the mobile carriers consisting of inert mobile ion exchange agents. Citric acid separations by liquid membranes removes the tertiary amines. So you can get your citric acid in the pure form, or you can use the microporous hollow fibers also. So permeators consist of two sets of identical hydrophobic microporous hollow fibers, and one set carries the feed solution of citric acid and other contains the strip solution. So usually the organic liquid membrane is contained in the shell side between these two sets of hollow fibers, and 99% of citric acid is being recovered by this microporous hollow fibers. So the hollow fibers means it's like a fiber having the hollow, it's like a tube, and it is having the two solutions, pre-coated solution. So in one set it carries the feed solution of citric acid, and the other is having the strip solution, means it will remove out the impurities. Stripping means it is removing the impurities, and the citric acid will be recovered from this at 99% recovery process. You can also use the electrodialysis method. Already I have explained you the electrodialysis. So electrodialysis enables the separation of salts from the solution. So there is a simultaneous conversion into the corresponding acids of the bases, and when you are using a electrical potential, and mono or bipolar membranes are usually employed for separating the citric acid. So these are the various recovery methods which are used for the citric acid production, but usually the method which is employing the concentrated sulfuric acid is mainly used for the recovery of the citric acid production. So what are the applications of citric acid? Citric acid is accepted as a GRAS, that is generally recognized as safe, and it is approved by the Joint Food FAO and WHO Expert Committee on Food Additives. So Food and Agricultural Organization FAO and World Health Organization. And citric acid monohydrate is widely used as a preservative for the blood storage. Then it is a flavor enhancer, it is a sequestrant, it is emulsifying agent. Then for adjusting the pH, it is used for the carbonation purpose also. So in food industry, it is used in various food products like making jams and jellies. It is used as a gelling agent, tartness and flavor is given. Soft drinks, acidulant, natural fruits flavor, tartness is given. And in frozen fruits, it inactivates the oxidative enzymes, so it protects the ascorbic acid by inactivating trace elements. Then in animal fats and oils also, it shows synergism with other antioxidants, and it is used as a sequestrant. In dairy products also, it is used as a emulsifying, acidifying agent. In cheese products, it is also used as an antioxidant. In cosmetics, it is used for pH adjustment, antioxidants and buffering agent. And in wines and cider, it is used for preventing the turbidity. It prevents the browning in some of the white wines. Also, it adjusts the pH and inhibits oxidation. In fruit and vegetable juices, it is used as a stabilizer, and in pharmaceutical industry, it is used as antioxidants, anticoagulants and acidulants. So these are the references. Thank you.